Alright, so welcome to Lecture 11, General Relativity. This one is on the equivalence principle and the manifold concept. So I'll cover a fair amount of ground in here, and probably if you haven't had a course in differential geometry or manifold theory before, maybe this will be too fast for sure. So let's get to it. So this is from chapter 2 of Sean Carroll's book, basically. And to start with, he talks about the equivalence principle, which of course led Einstein to discover or create general relativity. The story starts with the concept of weak equivalence. The weak equivalence principle essentially is summarized by the statement that gravitational and inertial mass are equal. So if you've had a good classical mechanics course, you've probably talked about this for some time, and indeed done some soul searching about exactly what do Newton's laws actually say. But this is basically it. You know, the force is the mass times the acceleration, where mi is the inertial mass. But on the other hand, the force of gravity is something like minus mg times the gradient of the gravitational potential, and here mg is the gravitational mass, or you might call it gravitational charge if you want to be really smart sounding. And anyway, the weak equivalence principle simply says that these are equal. So you kind of take it for granted. Mass is mass, right? But there it is. Now, if you look at this, then you can see, oh, okay, well that means that the acceleration, right, is minus the gradient of the potential, the gravitational potential, or the gravitational field, you might say. So acceleration, we see, is independent of the mass of test particles, which means that there's no, well, for one thing, there's no plus or minus gravitational charge, unlike electrostatics, right? So the acceleration due to gravity is what it is. It's a consequence of this field, and that's it. So another way you can reformulate the weak equivalence principle is this. He says, and this is all from Carroll, and if there's any mistakes in what I'm saying, it's all his fault. No, that's not true. I'm trying to summarize what he says, and there is, of course, more physical motivation, which sometimes to me seems like lying, but what can I tell you? The motion of freely falling particles are the same in a gravitational field and a uniformly accelerated frame in a small enough region of space-time. So the classical, thought experiment is if you're in outer space and you're in an elevator in a spaceship or something, right? And that elevator's going up at 9.8 meters per second squared, that would feel to you just like it feels to you to stand on the ground, right? Either way, you'd be facing, your shoes would have a normal, normal force back up, mg, where g is 9.8 meters per second squared, right? Because assumably you're not going through the floor, right? So the third law, the gravitational force down has to match the normal force up, and then in the elevator in space, the normal force of the elevator has to match the, the force that your shoes are putting on the elevator has to match the force that the elevator is putting on your shoes, right? There's no gravity. But anyway, this starts to fall apart if your elevator's too big, and then you can observe sort of like the inhomogeneity of the gravitational field. You can start to see these so-called tidal forces, right? So too large a region gives tidal forces, which correspond to inhomogeneities in the gravitational field. And so this concept of equivalence of gravitation and an uniformly accelerated frame, it is a local concept, right? It can't extend it too far. All right, so what else can we say? So Einstein, equivalence principle, or the sorry, I'm an idiot. You can think about a physicist in a box, and it's basically, all right, Sorry. It is raining at the moment. Maybe you can hear it. If you can, I'm sorry. But hey, it beats leaf blowers, right? Or ambulances. I do hear some crickets, but mostly leaves blowing in the wind. So here goes. The Einstein equivalence principle, the EEP, says this: in small enough regions of space-time, the laws of physics reduce to special relativity. All right, so it is impossible to detect the existence of a gravitational field by means of local experiments. So, I don't know. I tell you what, like, something is lost in the words that I've written on this page here for this idea, because, here, check this out. We're, like, here it is. Check it out. Oh, look, local experiment. Seems like gravity to me. So I think what it's saying is that you can't be sure when this thing drops, right? That I'm not in a space elevator that's going upward, and this is just because the elevator floor is pushing the table up to reach the thing when I drop it. I'm going to break it. Let me drop something less consequential like this marker. See? Marker drop. Yeah. I mean, so, I don't know. It seems like that's kind of a local experiment, and I can definitely see gravity like that, But I guess the thing is, I can't tell the difference between whether or not it's really gravity, pulling on the marker, making it fall, versus I'm in an accelerated frame, But man, even that I have a hard time with, because, well, I don't know. Something seems, maybe there's another sentence that could be added here which would make me believe it more. But I guess that's the idea. All right, anyway. So the Einstein equivalence principle implies that we must attribute the action of gravity to the curvature of space-time. What? No, there's a jump if there ever was one. So, fine. I think this sentence right here will come to life in Chapter 3, not in Chapter 2. This is just forward-looking. We're going to see that you can give curvature to space-time, and in so doing, reproduce the equations that we know and love from classical mechanics and Newtonian gravity in the appropriate limit. And as such, it becomes a viable theory of gravity, especially when you then can later verify experimental tests such as gravity waves, very recently, or aberration of starlight, the bending of starlight around sun or star, right? That was measured possibly by Sir Arthur Eddington back in the 1920 or 1919, I guess it was, or 29, I don't know, somewhere back in there. Although I think there's speculation that he didn't really observe it, he just, I don't know. There's always some kind of controversy. Controversy. Stupid Jimmy Fallon and his mispronunciation of controversy. But anyway, back when I actually used to watch late night. Okay, so my point to you is just this, that eventually we're going to make sense of this sentence, and it's not yet, okay? Fine. So special relativity, measure acceleration of charged particles with respect to a family of inertially related frames of reference. That's, in a nutshell, like something we could do in special relativity, right? You have inertial reference frames, and you can do Lorentz transformations to other inertial reference frames, and they're not really local reference frames either, right? In principle, they go on and on forever and ever. But in contrast, Einstein's equivalence principle says basically there's no such thing as a gravitationally neutral object. So to judge as the benchmark against gravitational acceleration, excuse me, I can't read my own sentence. There's no such thing as a gravitationally neutral object to judge as a benchmark against gravitational acceleration. Hence, acceleration due to gravity cannot be reliably defined. What? I mean, I read that sentence and I'm like, acceleration due to gravity can't be reliably defined, and I just come back to, what about this? 9.8 meters per second squared, dude. I don't know, like, these sentences need some qualification. So I think it can't be not reliably defined when you stack it up against the thought experiment of, are we actually all in some giant space elevator, and things are just deceiving us. We're actually in an accelerated frame of reference. So because basically any force which is proportional to mass, if we have the equivalence of mass, gravitational inertial mass, then we could understand any force which is proportional to mass as being a frame effect. See, because mass times acceleration is what you get from an acceleration, right? And that can be interpreted as a force from a certain perspective, right? We've experienced this in cars, right? You go around a corner, you feel the cornering, right? You feel the car pushing against you because, of course, you want to go in a straight line, right? You don't want to turn. You want to just fly off on that straight line motion. So that's another example of a frame effect, right? And that frame effect force is proportional to mass. So since gravity is proportional to mass, stands to reason gravity could also be a frame effect. That's kind of the argument in a nutshell, I think. So another thing to notice here is there are definition, unaccelerated or freely falling can be made, and particles only under gravity's influence alone will be unaccelerated in this understanding. Man, I must have had another sentence in my head that I didn't write down. Sorry about that. So I think what I'm saying here is that unaccelerated or freely falling means that the only thing, that they're only under gravity's influence, all right? And in this new way of thinking, we're going to say that those are unaccelerated, which, man, that's really weird, because it says, like, that's unaccelerated, you know? How wackadoodle is that? Uh-oh. The rain seems to have picked up. Well, I think I'm going to go in now. I'll be back.